Good morning, everyone. Thank you for showing up for your learning. Today's topic, we'll be looking at graphing the sinusoidal functions. So we are here on day 2, and you should read this comic first and follow along with the comic on Desmos. And now we're going to be here looking at the special triangles in the unit circle. Our goal is to graph the periodic functions. So you might be wondering, why are we going back to special triangles in the unit circle? They're actually going to help us quite a lot. So let's take a look. This is what we're looking at, our cool wobbly sinusoidal functions that do these kind of kooky things around the xy plane. And the unit circle here, and I'll leave this one up, it's a completed one, and I'm going to do mine in color for you. The unit circle is very useful for graphing the sinusoidals because, I'm just going to move myself out of the way up here, because if you recall, the unit circle, well, I'll show you in just a moment with another tool, but here's the unit circle going around in a circle. Here it is at 0 degrees, 90, 180, 270, and back to 0 degrees, 360 or 0. And you'll notice that the horizontal displacement here is what's being tracked by this blue dot. See, this is the horizontal displacement. And if we rotate that around 90 degrees, that's showing us the cosine curve. So when we remember from our trig that cosine is 1 when the angle is 0, and we'll see there, boop, that's when it goes through 0, and also at 360. And then over here, this red dot is tracking the vertical displacement as this goes around the unit circle. That gives us our sine curve. All right, so these are called sinusoidal functions, periodic functions, trigonometric functions, and also circular functions. There's lots of different names for the same thing, okay? So yeah, so this is the connection to the unit circle. So let's go ahead, and you're going to open up your unit circle. Well, let's actually take a look first at our special triangles, because they're going to help us to fill in the unit circle that we want to fill in. So the first special triangle that we'll look at is the 45-degree triangle. So you want to have a good sense for this one. It's an isosceles triangle. If this side length is 1, then this side length would also be 1 because they're the same. They have the same lengths there and there. And then 1 squared plus 1 squared equals, well, 2. And so this side would be the square root of that, because a squared plus b squared equals c squared. So then this would be the square root of that to get c. So that would be root 2. Okay? So we could take the square root of both sides. So what trigonometric ratios does this one give us? Well, any of the trigonometric ratios that are associated with a 45-degree angle. And so when we're looking at the unit circle, we'll see that those come like the cross lines like that. So here we have that special triangle, very useful to us. Another special triangle that we're going to be using is this 30, 60, 90 triangle. And this one gives us side lengths of, if A is 1, okay, then we don't need to worry about this A here, this A here, this A here. That's just a reminder that you can scale this up. So this is 1. And so if this side length is 2, then this side length would be 1, and this side length would be the square root of 3. And the way we get that, if you recall, is you can just take an equilateral triangle. I'm going to try and draw that again. I'm going to draw it in a different dimension, actually. If I take this equilateral triangle here, and I say, well, let's call this side length 2, and then cut it in half. So this was side length 2, but now I cut it in half, so I got a right angle there, and that's now side length 1. And so then I would get an equation like 2 squared, because that's the hypotenuse, is equal to 1 squared plus this side length. I don't know what it is yet. I know what it is, but maybe you don't. Call it a squared. And then you would solve this. So this is 4, this is 1, and I'm going to subtract 1 from both sides. So I get 4 minus 1 equals a squared. And so 3 equals a squared. So then this would be the square root of 3 on that side. So that's how you would remember this when you forget. Okay, just use your grade 9 Pythagorean theorem and cut an equilateral triangle in half. All right, so this gives us our primary trigonometric ratios for 30 degrees. So let's take a look at those. If we look at sine 30, that would be equal to opposite over hypotenuse. SOHCAHTOA, so SOH. So we have opposite over hypotenuse is 1 over 2. And then cosine 30 is adjacent over hypotenuse. So in exact values, that's root 3 over 2. Now, when you're looking at your calculator, and you punch these on your calculator, if you have a really fancy calculator, this is what it's going to tell you. If you don't have that fancy calculator, it's going to tell you 0.5, which is fine. And this one's going to tell you 0.866 something something. Okay, and that's also fine, but it's not an exact value. It's always rounded, even when you take all the digits the calculator can show you, because that goes on forever. This is an exact value. So it's one we use. And then tangent, of course, we can put tangent on there. And tan 30 is equal to opposite over adjacent. So that's 1 over root 3. I don't happen to know that offhand what that is, but you can ask your calculator if you care. All right. So that's opposite over adjacent for tangent. And then we can, of course, do the same thing for our 45-degree angles. So let's do those now. So I'll do those in another color. We're going to do those in our orange color here. So looking from this angle out, we have sine is opposite over hypotenuse. So sine 45 is equal to 1 over root 2. Cosine 45 is the same because the adjacent and the opposite are the same. Cosine is this number over that. So that's 1 over root 2. And then tan 45 degrees is equal to opposite over adjacent, which is 1 over 1. These are exact values. If a question ever asks you for exact values, you need to think about these triangles and use these triangles. So that's tan 45. And then it's the same from both sides. But up here, we have another triangle that we can look at. And that's this 60-degree triangle. If we look from this angle, if this is the angle of interest and that's not the angle of interest, then we're really thinking about, and I'll draw it here for us in yet another color. So we're going to use, we'll use green for this. So if I have this triangle here, where this is 60 degrees, this is 2, this is root 3, and this is 1. 1, 2, root 3, okay? So that one is the longer side. Here's my 90-degree angle, ostensibly. Now, looking from there, I can create sine, cosine, and tangent for those angles as well. Let's just move me out of the way. You're always in the way, Mr. Jennings. So over here, sine 60. Well, that's opposite over adjacent. So that's actually, it's cos 30. It's the same thing. Isn't that interesting? Sine 60. So root 3 over 2. Cosine 60 is equal to 1 over 2. Oh, isn't that interesting? We had that up there, sine 30. Okay, 1 over 2. Okay, and then tan of 60 is root 3 over 1. So it's just that one flipped. Cool, eh? Okay, so tan 60 equals root 3 over 1. I'm not going to write the over 1 because when we're dividing by 1, we don't usually write that. Okay, I'm 42 divided by 1 years old. A fancy way of saying my age. Okay, so those are our special triangles. And now we can use that to fill in the blanks of the unit circle. So you have one of these on your handout, and it's down here. And I encourage you to fill that out with all of the different values for the endpoints of these points. Wait a minute, how do I do the endpoints of points in the unit circle? What? Well, let's take a look at something here. Something's really going to help us. If we look over here, here's the unit circle, and it goes around, and it determines the values of sine and cosine. But this is pretty weird. Let's take a look at it over here in the unit circle here on Desmos. This is a graph that you can access by going to Desmos. You click on this tab. Oh, yeah, that's right. You click on this tab over here, and it gives you a whole list of, if you have any things saved, then you can look at yours. I have Mr. Wiggly Mustache and the Ferris trigonometry that I'll scare you with later. But down here, if you come down to trigonometry and you click on unit circle, it will open this graph and you can take a look at it yourselves. And over here is the unit circle. Let's take a look at it. So what are we looking at here? So this black point that's going to be going around the unit circle when I animate it. Oh, and another trick is here, for some reason, they set the animation to go from negative 10 degrees to 360. Set that to 0, and then this to 360. Just a little prettier when you say play. As this point goes around, you'll notice that we're tracking horizontal displacement and vertical displacement with this triangle. And and you can make this go all the way around in a circle that way. Yeah, okay. So anyway, just to get it to animate in a full circle. So how did they create this point? Well, that point's given by cos A and sine A. Okay, this is the x-coordinate of that is cosine. The y-coordinate of that is sine. Right? And we can use this to graph our trigonometric functions. Okay, one moment. It's the first day of distance learning, and all through the house, not a creature was stirring except for Mr. Jennings and his daughter, who's up at 5:30. Let's keep going, everyone. So, yeah. So what are we talking about? So over here, it's over here, Mr. Jennings. It's right there. All right, there we go. So this is a 30-degree angle. So we're going to do all of our 30-degree angles first in blue. Here, this one, 30 degrees, right there. So I'm going to write 30 up here. I'm actually not. I wouldn't say just write it down there because you'll get too cramped. But so that's a 30-degree angle. And then the value of sine can go here for the vertical displacement. Why? Because if we drew a triangle down here, we're not necessarily going to, but if we did, the height of that triangle would be a half. The distance here would be √3, and the length of this would be 1. Okay, oh sorry, this was √3 over 2, and this is 1, this is 1/2. So this, look at the special triangle, Mr. Jennings. So over here, you have sine 30 is 1/2. All right, and let's take a look at how we get that down here. So this is 30 degrees. Oh, it's too late to re-record. Okay, so here is 30 degrees. All right, if this is 1, then this would be 1/2 high. Because here, if this is 2, this is 1 high. So imagine I now scale this down to 1 and 1/2. Okay, so this is 1, and this is always 1 in the unit circle. So the value here would be 1/2. This point here is 1/2 the distance to 1 up here. This is 1. Yeah. And then this one, this is √3 over 2, because the x value is given there by cosine. This would be √3 over 2. Now, this is 0 degrees over here, and we'll do these in black, actually. We'll do all of our 90, 180 and whatnot in black. So this is 0 degrees. This is x is 1 and y is 0. This is the value of sine for 0 degrees. This is the value of cosine for 0 degrees. Here, 90 degrees. And this is 0, 1. So the value of cosine 90 is 0. The value of sine 90 is 1. Okay? Over here, 180 degrees. And this, the value of x is -1, y is 0. The value of cosine is -1 for 180. The value of sine for 0. Sorry, sine of 180 is 0. Okay, and then down here, this is 270. and the value here 0 for x, negative 1 for y. And so these give you your sine 270 is negative 1, cosine 270 is 0. Yeah. And then coming back around, we've done those. So now let's go back to blue and we'll put in all our 30 degrees. So if you recall, we have this concept of related acute angles. This angle is going to be related to that angle. This is 180 minus 30, and so that's 150. It has the same, you'll notice it has the same y value. So we can just put in this y value of 1/2, but it has a negative x value. It's just the x value has been reflected in the y-axis. So we have negative root 3 over 2 there. And then down here, if we flip it, this one down here is also a related acute angle. This is 210, 180 plus 30. And that will have the same x value as that. So it's negative root 3 over 2. And then the y value is just the negative 1/2. Okay. Now, these, and then let's do the last one here, 330. This is 360 minus 30 degrees. So that's 330. And it has the same x value, root 3 over 2, and the negative y value, negative 1 over 2. Okay, so these are the values of sine and cosine for these angles. So for 150, the value of cosine is negative root 3 over 2, and the value of sine is 1 over 2. And now let's just go back and take one more look here. See, cosine is giving us the x value, and sine is giving us the y value of this point that goes around the unit circle. Okay, let's carry on. So let's go back here. Now, let's take a look at, and we were using orange for our 45 degree angles. So let's fill those in orange. All right. Here you have this 45 degrees. And this one here would be 1 over root 2. And this would be 1 over root 2. Why? Because here, the value of sine and cosine for those two is 1 over root 2. So those are both 1 over root 2. You see it's a little bit bigger than 1 over 2. It's risen from that point, but it's also shorter than root 3 over 2. So it's over there. Okay. Now we can reflect that around here. This is 180 minus 45, so that's 135. This would be a negative 1 over root 2, and this would be 1 over root 2. Because it's the same height, so the y value is the same, but the x value, so the negative has been reflected. Now your calculator may tell you that this is root 2 over 2, but if you're very astute, you'll know that that's exactly the same thing as 1 over root 2. So that's just an interesting thing to remember. All right, and now let's reflect those around. So we have down here 225. And this would be negative 1 over root 2, negative 1 over root 2. Just applying my cast rule. Cosine is positive over here. All of them are positive over there. Sine is positive over there. And only tangent is positive down here. But tangent doesn't determine any of these. So both of these are negative because both sine and cosine are negative down here. Okay, and then the last one, 315. That's 360 minus 45. So over here, and this one, cosine is positive, so we're going to see 1 over root 2. That's the value of cosine 315. And then sine is negative, so negative 1 over root 2. And it's just a negative translation of the y value there, straight down here. Okay, last ones to do are green. And those are our 60 degree angles. And those are just flipped versions of this. It's like I just take these two and flip them to go up there because I'm just looking at the triangle from the other side. The 30 degree triangle, that is. So here's 60 degrees, and we know that this is 1/2. So the x value there, this is traveling 1/2 of this radius towards 1, so that's 1/2. And then if I go up, I'd be right there. And then this is root 3 over 2, that one. Now I can reflect that over here. This is 180 minus 60, so that's 120. And this will give me negative 1 over 2. And root 3 over 2. And then down here, translate that down here. This is negative 1 over 2. And negative root 3 over 2. And then over here, oh, and this is what angle? That's 180 plus 60, so that is 240. And then I add a 60 and then a 30 and another 30. So this is 360 minus 60, that's 300 degrees. And this will give me 1 over 2, because cosine is positive here for 300, and negative root 3 over 2, because sine is negative for 300. So now we have all of our values of sine and cosine for all of these different angles. And we're going to use that in the next lesson to plot the, to graph these parent functions here, sine and cosine. All right, everyone, see you in the next lesson.